Welcome. When you teach chemistry, you have to have some place to start. And typically when you start with a course in middle school or a course in high school where you learn certain basic kinds of ideas. Those basic kinds of ideas actually were evolved over the course of several millennia with lots and lots of people doing a lot of work. When I think about what I would want my first slide to look like when I do a chemistry course, I keep coming back to the idea that it's this book here by Linus Pauling, published in 1939. It was a book called The Chemical Bond. That's a pretty profound idea, the chemical bond. And in fact, what we're going to find is that pretty much this entire course is about the bond. What is the bond? The bond is the idea that you have atoms, and yes, that took a long time to figure out. But once you have those atoms, they have to come together somehow and make a bond, because when you can make that bond, you can start to make matter, which makes all the people here in the room. Until then, it's just a bunch of atoms flying around a sun. Now, what are the different pieces that we need to think about when we're putting together this bond? Well, one piece of them is to understand what matter is. And matter, in its most elemental form, as we know, is sitting on the periodic table. It's those 100 or so elements that will come together to make our bonds. Another important piece, though, is the part that has to do with being able to count, with being able to do math. So much of chemistry is about the ability to figure out quantitatively what is going on, how much matter is actually reacting, how much matter is actually involved in whatever it is we're trying to do. In this first video, what I'm going to do is take us through a couple millennia of exciting things that happened in chemistry. And along the way, as I do it, we will learn about what it is that people thought step by step to get to the point where we get to, in the 1900s, the idea that there are atoms that we can work with to make the chemical bond. Now, when you think about who the first chemists were, they actually lived several thousand years BC, and these were individuals who had one of two choices. The choices were either to stare up at the sky and look at stars, or to throw stuff into fire. Those were the two options. When you throw stuff into fire, it burns in most cases, if it's organic, but if it's a metal, it has the ability to melt and to smelt and to make ultimately a very new kind of compound. This is metallurgy and the creation of bronze. Suddenly you had a Bronze Age, and in that Bronze Age you made weapons, and well, the rest, as you know, is history. When people got better at using fire, they were able to create the Iron Age. The Iron Age took higher temperatures and it created a better material for being able to do work, and this took place in 1,000 years BC. Along about that time, a bunch of people started thinking deeply. These were philosophers, and these philosophers tried to figure out what matter was. And there were lots and lots of different arguments about it. One guy mused, and in fact he called it amusing, around 400 BC, that perhaps matter was made up of individual atoms. An atom is something which cannot be cut. Well, he made this argument. He didn't particularly care about it. It was speculation. Aristotle disagreed with him completely, but in neither case did it matter much because although they were early thinkers about the subject, they weren't doers, and they moved on to other things. Now, if I asked you who the father of chemistry actually is, not those people who throw stuff into a fire, but people who stop and create sophisticated tools, you would probably be surprised to find out that it was a Persian named Hayyan, or Geber in his Latinized name. This man, around 800 BC, actually created a collection of chemical compounds from different kinds of experiments using different kinds of laboratory equipment. So you go back and you look at a study of this man, he actually created techniques that involved things like glass beakers and distillation setups that he could use. And with this, he was able to synthesize lots of different kinds of compounds. Now, several hundred years later, in 1500, there was a substantial argument taking place. And the argument that was taking place had to do with whether or not chemistry was actually this thing called alchemy. Alchemy is this kind of metaphysical notion that you can somehow take matter and transform it into something else. And you can see how this came about. This came about because people threw tin and lead into fire and made what looked like gold when they were making bronze. So people thought, hey, this is a get-rich-quick scheme. Let's see if we can find some way using alchemy to make these valuable metals. And in fact, that's what most of the scientists of the day worked on. However, there was this renegade group out there, led by people like Bacon, who introduced the scientific method, and then Boyle in 1600, who argued for a very different way of seeing the world. And in fact, this book right here is actually about his disagreement with alchemists as he sets the stage for Boyle's law and for a much more quantitatively robust way of understanding science. Other scientists came along in the late 1700s. Lavoisier was able to actually isolate oxygen and use it to combust compounds. Lavoisier was able to create, using calorimetry, a good idea about the energy content sitting inside of compounds. Volta in Italy in the late 1700s created the first electrochemical capabilities that people would have. This all pointed towards a really important time period around 1800 when all of this came together with several very important individuals making arguments that allow us to define effectively what high school chemistry is today. Here's Proust. Proust is a man who, in mixing chemicals together, came to the conclusion that they came together in definite proportions. By that, he was suggesting that it would take two hydrogens and an oxygen to make water, and that was definitely water and nothing else. Around 1800, Dalton, as he was creating the idea of atomic theory, the idea, as Democritus had proposed, that those particles could in fact be individual and uncut, also came up with the idea that the weights for those atoms would actually be in definite proportions with each other as you formed molecules. And then, an individual that we have all come to hate, Richter, came along and proposed the word stoichiometry. The word stoichiometry is a word synonymous with having to work terrible problems in high school chemistry. And we're going to have to look at that and understand it a little bit. I thought I would bring some of my students out on stage to get you a sense of what stoichiometry is about based upon the law of definite and the law of multiple proportions. So if I could have a couple of hydrogens and an oxygen come out, we're going to look at what is not an amazing observation, but it was back in 1800. Here's two hydrogens, here's one oxygen, two hydrogens, one oxygen. That's it. That is water in that simple 2-to-1 proportion, whether that proportion is done by counting or whether that proportion is done by weight. That is water. If we added another oxygen, you end up making a completely different compound. It now has a 1-to-1 ratio of hydrogen to oxygen. This is hydrogen peroxide. Water is the stuff you drink. Hydrogen peroxide is the stuff my mother used to pour in my ear to get rid of the earwax. So if I take away that oxygen, I'm back to having water. Notice these ideas of conservation are in play. I had 2 atoms to 1, and that number remained. I added another one, it was 1-to-1, and that number remained. Now, I have the opportunity to do chemical reactions. So I'm going to create a couple of hydrogen gas molecules out here and an oxygen molecule out here. So let's get a couple of hydrogens and a couple of oxygens. Notice we have 1, 2, 3, 4 hydrogens. We have 2 oxygens. That's what's definitely there. They are there in what we will understand as 2 hydrogen gas molecules and 1 oxygen gas molecule. And I'm going to ask those to react. When they react, they are basically doing the equivalent of a hydrogen balloon explosion that you see in here many times. Now notice that when it occurs, all 6 of these individuals are still on stage. One of them isn't heading off to the bathroom or something like that, as people used to think would happen, when matter would suddenly show up or it would suddenly disappear. But let's explode the balloon, go ahead, and let's make us a couple of water molecules. Notice there's been an exchange of those gas atoms around, but when they're done, I still have my 4 hydrogens and my 2 oxygens. This is the conservation of mass idea within atoms that is so profound and was absolutely essential for us to be able to set the table quantitatively for chemistry. Thank you. Now, what can we do with those examples that I just showed you quantitatively? We can do the thing called high school chemistry. High school chemistry talks about the idea of stoichiometry, where I have an unknown amount of matter and I have a known amount of matter. And then I use different kinds of conversions to be able to solve the equation to find my answer. I'm not going to do this particular kind of problem here, but this is what stoichiometry is, and notice that its foundation was built very much on the back of the idea of conservation of mass arguments and of the laws of multiple and definite proportions. Now, while those individuals were doing that math, they were doing gravimetry to be able to weigh stuff and to count stuff, there were other folks having more fun. Davy, around 1800, was using electrochemistry basically to find all of these elements in the periodic table that people hadn't known about before. So for example, he was able to give us the alkali metals and the alkali earths that he was able to identify electrochemically, and he did a lot of work with halogens as well to be able to identify them. When he was all done, he had substantially contributed to the number of known elements. And then this man, Mendeleev in Russia, in the mid-1800s, came up with the first periodic table. That periodic table was a table built on the idea of atoms, and it was built on the idea that you could reduce those atoms to an elemental form that could be put into a table that would have a period to it. Now, this brings us up to the 1900s. This is what we know at this particular point. This is what high school chemistry has shown us. We have the ability to count atoms, we have the ability to conserve matter and do chemical reactions. But at this point, we don't know what's actually going on inside an atom. Because we don't know what's going on inside the atom, when I had those young men and women move around to make a hydrogen this or an oxygen that, it was my whimsy that made it happen. I couldn't explain why it did. What happened in the 1900s, what happened in the 20th century with the evolution of an understanding of the fundamental particles within an atom that could be cut, and with an understanding of quantum mechanics, set the stage for what it is that Linus Pauling was actually able to put into his book about the chemical bond.